Okay, so last day we started looking into incorporating calculus into our sketches. The question was sketch this graph, and we said these are sort of our basic steps up to this point. We have a mental picture of a quartic function. We always know it's got that W shape. If we remember the fact that it's negative, or sorry, not negative in this case, means it's W as opposed to an M if it were negative. We know how to calculate intercepts. Sometimes it'll be easy, sometimes it won't. If it's easy, we go ahead and do it, and we can incorporate them into our graphs. If it's too tough, we don't have to bother. Critical points, we call maybe turning points, or again, maximum minimum points. We can find by making the first derivative equal to 0. And then depending on the other information, we can set up a chart to help us find whether an individual critical point is a maximum or minimum. Or of course, if we already sort of have the basic mental shape of the graph, then we know, if we're starting in a decreasing mode, then the first critical point will be a minimum, and the next one will be maximum, and so on. So depending on what we know, we may not need all these pieces of information. This is the chart we can set up if we don't have the mental picture, or if we don't actually have a graph to work with. Then the idea of looking at what happens in the individual ranges between my zeros, is my slope increasing or decreasing, allows me to determine whether something's a maximum or minimum. So in this case, I'm decreasing to this point and then increasing after it. Clearly, -1 is going to be a minimum value. And this is sort of the graph we came up with. Again, a little bit messy. I was drawing it on the tablet, and that's my excuse. I could have done a better job for sure than I did, but you'll do a better job on paper. Now we're going to move into what's next, sort of second derivative. We'll come back to those diagrams in a second. So the second derivative gives us a little bit of an opportunity to do a bit more. Here's my first derivative from last day. Take the second derivative. Again, the actual math, the calculus, finding second derivative is usually going to be a lot easier because the equation is smaller, and usually with smaller, always with smaller powers. So I get 12x squared minus 24x minus 16. And then the rest of this is just going to sort of figure out what are the values of x that give us a second derivative of 0. Okay, now, of course, what we're interested in is what does a second derivative of 0 mean? And of course, that's what we're going to figure out right now. So if we go back here, this is the graph I drew. I could have done a slightly different thing here. I sort of have this graph kind of peeling off to the left. I could have done a little bit more of a parabolic nature to this. Same sort of thing here. If I'm coming up this side, I could have assumed that the graph was actually going to be kind of like a parabola coming in as opposed to a parabola going out. And that's what the second derivative is going to give us. It's going to give us a couple of options. The other thing to recognize is down here, I've got this kind of a pattern here. But at some point, my graph is going to switch to, that was a mistake. The graph is going to switch to being more of this shape. Okay. So this is what the second derivative is going to allow us to establish. This is what we call concavity. This is a graph that is concave up or opening up. This is a graph that is opening down, or sorry, a section of the graph that's opening down. Somewhere around here, there's going to be a transition where I go from being open down to being open up again. And then as we move out, my graph may or may not switch again to be opening down at this point. Same sort of thing over here. And the second derivatives give us these kind of, and again, maybe the word turning points is actually almost more appropriate here. Something like this, where I go from opening down to opening up, or again, somewhere in here, we'll have the same thing where I have a parabola that's opening up here, and then a parabolic shape that's opening down. At some point, that turn should occur. So if we look at the graphs on Desmos, kind of zoomed in, you can sort of see it a little bit better. This is the bigger part here. It's coming down, and then obviously somewhere around here, somewhere in this general area, my graph is going from being concave down to being concave up. Same sort of thing here. Again, this is the zoom, just the zoomed in of the previous one. It's opening up, sorry, and then somewhere right around here, it looks like, the graph is going to switch to opening down. And so that's going to be kind of the thing that we're finding now. How does the graph transition from this to this? Or where, more likely, because we sort of know what's going to happen, but where does it transition? So went through this, found the second derivative, determined the zeros, and so again, this is our maybe a better description of turning point than the other one. It's where I'm going from concave up to concave down, or vice versa. As always, if I know an x value for a point, I need to know the y value as well. And so to find the y values, sub back into the original, this point and this point, and I get a y value of negative 1.13 and a y value of 103. No, that's not right. That should be negative 103.67. Give me a sec. Okay, so yeah, negative 103.69 is approximately the value there. Now again, basically the same thing, and this time we probably won't be able to avoid it too much. Intuitively, again, we can get an idea what's going on. So essentially, these are my turning points, negative 4.3, 3.1, and as I did last time, I'm testing values in each of the ranges to determine whether my second derivative now, this is for the second derivative, whether the second derivative is positive or negative. And we should be able to see what each of those means. So my second derivative function down here, I put negative 1 in here, I get positive 12. Put negative 1 in here, I get positive 24. And then minus 16 means that I have a positive in this section. The 0, 0, 0, I get negative 16. And something greater than 3.1. Again, just sort of reminding you, what I'm doing is I'm testing any value from these different domains. Negative 1 is probably the easiest number to work with. That's less than negative 4.3, sorry, negative 0.43. 0 is, of course, the nicest number to work with always. And then something here, 10, 5, something that's going to be nice and easy to work with. And so here I put in a 5, I get 25 times 12. Here I put in 5, I get 5 times this. This one will be positive. And so if we go back to our graphs now, and I'll clear off the mess here. What we found was, leading up to our turning points, we have a positive value first. Okay, so this is, again, somewhere around here is the one turning point. We had a positive value previous to that. We had a negative value after that. And then we had a positive value after the second turning point over here. And so hopefully from that you can see in the first section here I have concave up, or open up. In the second section I have opening down, and third section I have opening up. And so that's what our second derivatives tell us. If I determine that we have a positive second derivative in one section, it means that the graph will have kind of a parabolic shape in that section that opens upwards. Negative opens down. So this is up. This is down. And again, up again. Now again, your first instinct is to say probably, well, I could kind of tell that from the graph, remembering we shouldn't know what the graph is ahead of time. But where it came into play here was on the end points of my graph. I sort of naturally just kind of let my graph curl off to the outside. But the suggestion there is that this is opening down based on the way I had drawn it. This would be opening down as well. And what we know is everywhere to this side of that turning point, which was negative 4.3, negative 0.43, should be opening up. And so I actually know now my graph did not look like this. It just was a nice consistent curve up here. Same thing with this one. A nice curve upwards here. Oops. So that's what our second derivative tells us. It allows us to determine where points turn, where these real turning points are. It goes from opening down to opening up, or from opening up to opening down. And again, just gives us that one more point, one more fixed point on the graph, so that what we're ending up with now is no longer so much a sketch, but actually a pretty darn accurate graph. Depending on the actual numbers, the example I gave here, I had negative 128, and obviously that's difficult for me to graph on the same graph with something like negative 0.43. But we are getting a series of fixed points. We're getting the idea of whether we're increasing to those points, decreasing from those points, and where exactly we're hitting and turning from that opening up to opening down. And so our graph actually is becoming extremely, extremely accurate at this point, to the point where I'm happy calling it a graph more than a sketch, other than the fact that we don't have to be so perfect when we're drawing them on a test or anything. We are getting a very, very accurate look at what the graph is. Okay, so I'm going to stop it there. We're going to allow you to try a few of those, and we'll see how it goes.